In this presentation, I will teach you intrinsic and extrinsic semiconductors. In the last lecture, I explained you how silicon and germanium forms 4 covalent bonds to attain the noble gas configuration. In this case, we have silicon atom, so we require 4 additional silicon atoms to donate 4 electrons so that we have 8 electrons in the outermost orbit. This structure we are going to use in this presentation also, but this one is little bit bulky, so I'm going to eliminate few things that will make this structure simple. I will not represent the nucleus and orbits like this, but I'm going to draw a circle, and this circle will represent the atom. In this case we have silicon atom, and to represent the silicon atom I will write Si inside the circle. If you want to make the atom for germanium, draw the circle and write Ge inside it. Now let's see how we have to represent these 4 covalent bonds. I'm going to represent them simply like this. The last thing that we have to see in this form of representation is electron. You can see we have electrons here, 4 electrons, and these 4 electrons we will represent by negative sign. So this is the easiest way to represent this structure, and we are going to use this form of representation instead of this one. So let's move to the intrinsic and extrinsic semiconductors. Here you can see the structure that I was talking about. We have 4 covalent bonds for every atom present in this structure, and in that way we have 8 electrons in the outermost orbit. This arrangement of atoms we call as lattice. This lattice is very important, and we have millions and millions of atoms present in this lattice. This is the lattice for silicon because we have silicon atoms here. In the same way, we have the lattice for germanium when there are germanium atoms present. Now we will move to the intrinsic semiconductor, what it is. Intrinsic semiconductors are pure semiconductors. What do you mean by these pure semiconductors? Here you can see the lattice for silicon, in which we have only silicon atoms. No other atoms are allowed here, and thus we call it pure. When there is no other atom present in the lattice, it is the pure semiconductor, or you may also call it intrinsic semiconductor. So this is the one thing that you should keep in your mind, and now you can easily distinguish between the intrinsic and extrinsic semiconductor. In extrinsic semiconductor, we have impurity atoms. We don't have only silicon, but we also have some other atoms like aluminium, boron, that we will see later. And the free electrons are only due to the natural causes. This is very important point. In case of intrinsic semiconductor, the free electrons, it means the electrons which are ready to participate in the conduction, are only due to the natural causes. The natural causes like light energy, thermal energy. When you give the thermal energy, the electrons present in the covalent bond will obtain the kinetic energy, and they will break this bond and will be available for the conduction. So we can say that with increase in temperature, the number of free electrons available will also increase. The next point is the temperature coefficient. Silicon and germanium both have negative temperature coefficient, and as you already know, in case of negative temperature coefficient, when we increase the temperature, the resistance of material will decrease. This implies that with increase in temperature, resistance will decrease. And in case of conductors, the metals, the temperature coefficient is positive, and thus by increasing the temperature, the resistance will increase. So here we have opposite of that, and you should keep this thing in your mind because sometimes they will ask it in multiple choice questions. So this is important. Now you already know intrinsic semiconductor, and you have idea about the extrinsic semiconductor. In this we add impurity atoms. We don't have only silicon present in the lattice, but other atoms are also present, and we call these atoms impurity atoms. So let's talk about this impurity atom first. 2 types of impurities are there. The first one is the pentavalent valent impurity, and the second one is trivalent impurity. Now we will first discuss pentavalent impurity. The pentavalent impurity are the atoms present in the fifth group. You have to refer the periodic table and locate the fifth group. You will find the atoms present there. When you see their atomic numbers, you will find they have 5 electrons in the outermost orbit. The pentavalent materials are antimony, phosphorus, arsenic. As is the symbol for arsenic. I hope it is correct. Let's see, As is the symbol for arsenic, and this is the fifth group. In the same way, if we talk about the trivalent impurities, then they are the elements of third group. They will have 3 electrons in the outermost orbit. It is very simple. So let me write down some of the elements from the third group. We have boron, gallium, aluminium of course, and indium. So these are the 2 types of impurities that we have: the pentavalent impurity, the fifth group element, and the trivalent impurity, the third group elements. So we add impurity atoms to intrinsic semiconductor or pure semiconductor to have extrinsic semiconductor. At what proportion we have to add these impurity atoms to the lattice? We add 1 part in 10 million. This means in 10 million atoms of intrinsic semiconductor, we add 1 impurity atom. In 10 million atoms of pure semiconductor, we add 1 atom of impurity or 1 impurity atom. This is very important. And the next thing that you should keep in your mind is the addition of these impurity atoms will totally change the electrical properties of the intrinsic or pure semiconductor material. The process of adding certain impurity atoms to the pure semiconductor is called doping. This word we are going to use a lot in this course, doping. Doping is the process of adding impurity atoms, whether pentavalent or trivalent, to the intrinsic semiconductor or pure semiconductor. This intrinsic semiconductor is pure semiconductor, and we dope this intrinsic semiconductor with the impurity atoms, and we have our extrinsic semiconductor. So this is the word that we use for the addition of impurity atoms to the pure semiconductor. Because of this doping, we get extrinsic semiconductor of 2 types. The first one is N-type. You must have learned these things in your 12th standard, the N-type semiconductor and the P-type semiconductor. In N-type semiconductor, and these both are the types of extrinsic semiconductor, right? And in N-type semiconductor we add pentavalent impurity, whereas in P-type semiconductor we add trivalent impurity. We add pentavalent impurity, and in P-type semiconductor we add trivalent impurity. So this is very important thing that you should remember, the types of extrinsic semiconductor. Now we will study how N-type semiconductor is formed. For this I will copy and then I will paste it. I will drag it down and we will see how we have N-type semiconductor. As I have already told you, in case of N-type semiconductor we add pentavalent impurity. So I'm going to add antimony, Sb, antimony, to this lattice, and I will remove this silicon atom. Instead of this I will have antimony Sb, and as I have already told you, the antimony, the fifth group element, will have 5 electrons in its outermost shell. So 4 electrons will be combined with this, and this silicon atoms. 4 electrons are combined in this covalent bonds, and we still have 1 electron left. So I will represent this electron with a negative sign. This one is the fifth electron of the antimony. Let me write this thing down. The fifth electron, the valence electron, the fifth valence electron of antimony. Okay, and as you already know, the electrons are the charge carriers, and because of this we have current through the material. So we have electron, and this is free electron. If I apply the potential difference across this material, then definitely this electron will be drifted and we have electric current. So in n-type semiconductor we have electrons as charge carrier. You should keep this thing in your mind. We have electron as charge carriers, right? In the same way, if you approach for the p-type semiconductor, then I will again paste this diagram, and I will add trivalent impurity. In p-type we will add trivalent impurity, and I will remove this silicon atom, and we will have the trivalent atom. Let's say it is boron. In trivalent we have 3 electrons in the outermost orbit or the valence shell, and these 3 electrons will be combined to, let's say, this silicon atom, this silicon atom, and this silicon atom. So this silicon atom will not get the electron to have the covalent bond, so there will be absence of electron, and we will represent the absence of electron by the hole. This is hole, and it is nothing but the absence of electron. Absence of electron. This hole is very important concept, and we will learn more about holes in the next presentation. Right now you have to know only one thing, that we have 2 types of charge carriers in semiconductor. The first one is electron, okay, and the second one is the hole. So in p-type semiconductors we have holes as charge carriers, whereas in case of n-type semiconductors we have electrons as charge carriers. We will see how holes act as the charge carriers in the next presentation. That will be very interesting and very important. I hope you got how we obtain the n-type semiconductor and p-type semiconductor. So if I make a semiconductor material that is of n-type, then let's see how it looks. We have the donor ions. I'm going to represent the donor ions by positive. Why we have donor ions? Because we have electrons, and the atom donating this electron will possess the positive charge, and we are representing them with this positive sign, okay. And we have electrons as majority charge carriers, so I will represent electron, so many electrons, because they are the majority charge carriers. And we also have some holes. It is not like we have only electrons in the n-type semiconductor and only holes in the p-type semiconductor, but we also have some holes in n-type and some electrons in p-type. So we will make p-type semiconductor material also. In this we have holes. So the atom having the holes, it means it is going to take some electron. It is going to have some electron from other atoms. So I will represent this by a negative sign, okay. And we have holes as the majority charge carriers. So I will make so many holes like we made electrons in this case. This is n type and this one is p type, and also we have minority charge carriers as electrons in this p type. So this is how we will represent the n-type material and p-type material. These are the immobile ions, or we will write donor ions. The electrons are the majority charge carriers, and in this case we have holes as majority charge carriers, and here holes are minority charge carriers, and in this case electrons are minority charge carriers. Right. So this is all that you should know in this presentation. The boron atom will get electron from neighboring atoms, and hence it has negative charge. That's why we are having the ions with the negative charge. So this is all for this presentation. In the next presentation we will study about the electron versus hole flow, and also we will develop the mass action law, a very important presentation. So see you in the next one.